nanohub.org.
You can follow along with this presentation using printed slides from the NanoHub. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
So today we'll be talking about reliability of MOSFET. This is a very important topic. Most of the time for last 10 lectures or so, we had been talking about how MOSFET operates, MOS capacitor, MOS transistor, how it operates. But most of the time what people do not realize that what makes a technology successful is not how much it performs or how well it performs initially in the laboratories, but how well it survives the harsh condition that it is supposed to operate over a prolonged period of time, many times for 10 years or so. And that is exactly what reliability of MOSFET, the physics of it, tries to describe. So I'll begin by explaining why this is a very important problem. Turns out one of the most important problem in MOS technology these days is the reliability of MOSFET. I'll explain why. We'll talk about three types of reliability problems. The most important one is something called a negative bias temperature instability. Now this you should distinguish between this bias temperature instability I talked about the sodium ion moving from within the oxide left and right, coming from human hand and how it was solved in 1960s to solve and make MOSFET possible, practical MOSFET possible. This is different. This is also discovered in 1960s. It went away for about 20-30 years, and then in mid-90s it resurfaced. And nowadays this is one of the most important reliability challenge for MOSFET. I'll talk about gate dielectric breakdown. As I said, that this is a very thin oxide that you have about a nanometer or so. And when you apply a voltage, 1 volt may sound small, but you see, if you divide 1 volt divided by 1 nanometer, you have more than 10 megavolts per centimeter electric field in there. If you look up in any book, then it will say at 10 megavolts, this should break down completely be destroyed. Yet our transistors do not get destroyed. And I'll try to explain very briefly why and how to think about that problem. Finally, this issue about radiation-induced damage, particles coming from sun and outer space, and as well as various environments. This is very important. Every time you take a transatlantic trip, there is a probability almost close to 1 that one of the bits of your flash memory drive will be flipped. So that if you take a PowerPoint or any file, your music file, it's almost certain that a few of the bits might be flipped. And the reason it doesn't hurt you, because there are error correction code that you have to put in every storage device now because of this bit flip problem. I'll explain a little bit about that also before concluding. Now the point I wanted to make in the beginning, that in this course you are learning about how MOSFET operates, right? And how to analyze them, how to think about surface potential, inversion charge and all. But of course, what you realize that these MOSFETs are under incredibly harsh conditions they operate. Then by the time you throw away a computer, almost all the transistors will have switched close to about 10 to the power 14 number of times. 10 to the power 14 is a very large number. It's like 100, 10 to the power 14 is about a, 100 million? Oh, no, not million. Okay, you get the 10 to the power 14. It's a large number. I forget how else to put it. And when you turn things on and off this large number of times, this is a hard disk reader that all of you have in your computers, and you can see on the periphery there are all input-output MOSFET transistors that essentially connect the output world, or the outside world, to the inside world of the microprocessor. And you can see that they have been lighting up. This is a liquid crystal image of the temperature, and they have been lighting up. That means those places are incredibly hot. And what will happen that when you use it under such a harsh conditions over a prolonged period of time, the transistors are going to degrade, and essentially eventually they are going to fail. And this is certainly not acceptable, because once you have this type of degradation, let's say the gate oxide, you remember the MOSFET, right? The MOSFET, the two vertical columns are source drain contact. The fingers, the black fingers coming from the two sides are source and drain. The very thin region in between, the thin region is oxide, and the black, little black strip on the top is the gate contact, so gate metal. So you can see that those regions are heavily doped, show us as black in this picture. And if you blow up that region, many times you will see the gate oxide has been completely blown because of the harsh operating conditions that the transistor finds itself in. Incredibly, the physics of this is actually one can calculate when things will break after a certain period of operation. That's the essence of the reliability physics. So in order to understand that this reliability, issues of reliability, you will have to distinguish between two types of bonds. One bond that I have already discussed is the passivation of silicon with hydrogen at the silicon dioxide interface. This is that forming as anneal. Remember that silicon dioxide cannot really satisfy all the bonds of silicon. Therefore, you need to tie up the extra bonds with hydrogen. Hydrogen has one proton, this has one dangling bond. So they make a covalent bond and everybody is happy. Now the thing is that something that comes easy also goes easy. That means that something that you did in the last process step with a low temperature, this hydrogen stitching up the substrate with hydrogen bonds, as soon as you begin to operate the transistor, some of the hydrogen begins to leave with the electric field, and I'll explain why. And as they begin to leave, what will happen that gradually the number of interface states will continue to rise again. Remember, you brought it down to 10 to the power 10, and gradually after the hydrogen begins to leave, the number will gradually go up, and if it reaches on the order of 10 to the power 11 per centimeter square, then you are already in trouble, because then your threshold voltage has shifted a lot and the current is no longer stable. The other type of bond that could be broken is silicon oxygen bonds, and that's the second bond that can also be broken. Now you will notice that in this list I didn't put silicon bond breaking. Why not? I mean, there are lots of silicon bond in the crystalline phase. Why not? Because crystalline materials are deposited at very high temperature. Their bonding is very strong, and they are in the crystalline phase. Everybody is where they are supposed to be, and therefore it is not easy to break it at room temperature, as you are just operating the transistor, right? In your computer, you are just using it in room temperature. Of course, then therefore it's not easy to break, but the amorphous material, those are randomly structured bonds, easy to break. Similarly, the silicon hydrogen bonds, easy to break. And that allows you to categorize the reliability problems into two broad groups. One is this broken silicon hydrogen bonds, and the negative bias temperature instability and hot carrier degradation. These are related to silicon hydrogen bond dissociation primarily, this surface dissociation. And if you have silicon oxygen broken bonds, right, in that case, those the various mechanisms that are associated with it will be called gate dielectric breakdown, electrostatic discharge, radiation-induced gate rupture, this type of thing. These are various things. I'll give you some examples. By the way, do you see this hot carrier degradation? It should be HCD, but it is called HCI. So this is hot carrier induced degradation, and so this the shortened version doesn't really go with the full name. And similarly, the gate dielectric breakdown, there is this extra T. This is because it is time-dependent dielectric breakdown, TDDB, and that's something these things we'll talk about. So I'll give you some examples. I will talk about negative bias temperature instability. I'll tell you a little bit about the physics. I'll tell a little bit about the gate dielectric breakdown and radiation-induced damage. Okay, so that will give you some flavor of how to think about this problem. Now, silicon hydrogen bond, as I said, that those are at the interface between silicon dioxide and silicon oxygen, within the bulk of the silicon dioxide, right? Now you remember how thin these things are, right? 6 atoms, 5 or 6 atoms vertically, and over a wafer, 12-inch wafer. So sometimes I may have given this example before, that if you cover the whole United States with 6 inches of snow, not an inch variation across the whole country. This is the level of control that you have to have in order to make an integrated circuit possible. Simply amazing that anyone can do this. And now we do it routinely, take it in our pocket on those flash drives and everything, and think nothing about it. And that's the amazing part of this technology. Let's talk about negative bias temperature instability. First of all, the word negative. So it happens with negative voltage, and it only happens in P MOSFET. Doesn't happen primarily in N MOSFET. What I have shown here on the left is an inverter. Now, I'm sure many of you may know what an inverter is, but for the time being, we'll assume that this is a PMOS on the top, series connected to an NMOS on the bottom, and together the input are connected together and connected to an input. Now, if we apply a 0 volt on the input, then what happens? Then the NMOS is off. Do you realize that? Because it has a positive threshold voltage, and at 0 voltage the NMOS is off, PMOS is on, right? PMOS is on, and as a result, the VDD, the supply voltage VDD, gets connected to the output VDD, output, and becomes equal to VDD, and that's why it's called an inverter, because your input is 0 and output is 1. Now, if you think about what is happening to the PMOS, then you will realize that the source drain is connected to VDD and the gate is connected to 0 volt. Now, if I assume that source drain is connected to 0 volt, then equivalently I would say that the gate is connected to a negative voltage, and that way you understand why the transistor is on, because the threshold is higher than the threshold voltage of the transistor, the negative voltage. This negative voltage, what it does, that it creates defects at the silicon-silicon dioxide interface between this yellow and the white region. And what it does then, that if you look at the IV characteristics, have you seen this IV characteristics before? This is that square law, or Vg minus Vt to the power alpha, which could be between 1 and 2. Now, the black line is before stress, meaning when you just bought your computer from your store, just bought it home, I haven't yet opened it. That's your black line. But what's going to happen, and something that you don't expect, is that as you are writing your Microsoft Word, various documents and other things, gradually the current, the output current, will gradually come down, and it will become the rate curve. Over a period of time, it will become the rate curve. And this change in the current, in the drain current, you can take it and divide it by the original current. So that's the percentage change, right? That's the percentage change. And if you look at the percentage degradation as a function of time, so you see 10 to the power 1 second. What is this red line, 10 to the power 9 seconds, around 10 to the power 9 seconds? So it is close to this 10-year lifetime. So what is 10 year? 10 year is 3 times 10 to the 8. I think that's the 10-year, so many seconds in 10 years. So many times your computer will be guaranteed for 10 years. So that's your warranty period, or guarantee, whatever is the manufacturing period. And what you will see, that the black curve will gradually come down, and the rate curve, if you look at the difference and plot it, then the degradation will continue to increase. Do you understand that as this curve is going up, there on the right hand side, that means the rate curve is going down, right? That's the difference divided by the original value. That's the degradation value. And what is amazing, that this curve is generally, if you plot it on a log-log curve, it becomes a straight line. I'll explain the physics in a second. But you realize that if it crosses 10%, exceeds 10% degradation, so the rate curve is way down by 10%, then the circuit you have designed, assuming a given level of current, that circuit will not work anymore, because the transistor, the preceding stage of the transistor, will not be able to supply the current in succeeding stages. And so your computer is going to die. You can always blame it on the software, and you can say that that's why your computer died, but many times the hardware may be the problem as well. Now, so therefore, we have to understand how it degrades and how long will it take, because you realize that if it degrades that much and all of a sudden a million transistors is returned, then the company, whoever made it, they will go out of business. So this physics, explaining or estimating how many will come back as a field return of a computer, is of primary importance when you design a MOSFET. Now, as I said, that if you look at the delta VT, the threshold voltage shift as a function of stress time at various temperature, 25, 90, and 150 degrees C, then you will see that on a log-log plot, this has a straight line. I'll explain that in a second, but let me first explain what am I talking about delta VT. Delta VT is essentially when the black curve came down to the red curve. It's because its threshold voltage changed. Now, why did its threshold voltage change? Because as the hydrogens are diffusing away, you have more defects. Those more defects are catching more electrons. That causes a QF. Do you remember the QF and QIT? So it increases the QF and a QIT. As a result, then your threshold voltage changes, and therefore your current changes. So this tells you how much current change there would be. Now, for NBTI, this threshold voltage shift is given by this very strange formula. You have a constant and exponential dependence on temperature. You see, if the temperature is high, then the degradation is more, right? So you can see that that's exactly what is seen, that 150 degree, the triangle down, that is significantly higher than the 25 degrees C, that's the triangle down. Now, why does 150 degrees C, I mean, nobody, even in the equator, there's no 150 degrees C region where you want to live at least. Why do I care about this higher temperature? The reason is, yes, not in the equator, the environment may still be room temperature, but inside the computer, remember, as they are turning on and off, each transistor are getting incredibly hot. This is dumping energy. So the transistors around them can have significantly higher temperature than your room temperature, right? That's why your computer often gets hot. Your room may be cold, but your computer gets hot. So this high temperature is important. The amazing thing is that many times this is described by a power law. Power law means that something raised to the power a constant, time raised to the power a constant, power law to the power 0.25. And amazingly, this should happen over many orders of magnitude. It could happen over 6, 7 orders of magnitude in time, and this quarter power law will keep going, keep going, keep going. And so this is a very robust and unusual type of degradation. And if you apply larger electric field, then your A will depend on the electric field. So therefore, as you're turning transistors on and off, your degradation will change with respect to the voltage waveform. Now, before I explain why this is a T to the power 0.25, remember this is a hydrogen. We are talking about silicon hydrogen bond dissociation. We are not talking about electron holes anymore. We're just talking about how bonds break. So we want to explain to you how this happens. But before I do that, let me explain something about diffusion distance, right? Now, this is something you have seen many times. And so I really don't have to explain too much. If you put a drop of ink in water, then you know that the ink spreads. And it spreads why? Because the molecules in that drop of ink, they have a random motion. They go in various directions. And that's what I'm trying to show. The red point is a sort of a drop of ink, with many molecules, and they will have a random walk. The white jumble regions are sort of the molecules moving around. Now, how far do they spread over a given period of time? You know this, right? It's square root of dt. That is how far it goes. And how does it work? That if you put a drop of ink like this, then in the beginning it's very tightly focused over a very small region, and then you look at it a little bit later, it has spread a little bit more, and you look at it a little bit later, it's spread a little bit more. And I don't want to go through the math, but essentially how far it will go on the average. This will be square root of dt, and that's the x is proportional to. There will be maybe a factor of 2 or 4 upfront, but I'm not including that yet. By the way, so this is the diffusion coefficient of the molecule, whatever molecule. It's not electron holes. This is whatever molecule we are talking about. If it's the ink, then it's the ink molecule, diffusion coefficient of that. Okay. Had it been ballistic, then of course with time, it would have gone linearly proportional to time. There wouldn't have been a square root. Because of this back and forth, scattering back and forth, it cannot go as fast as it would have gone, as far as it would have gone in ballistic case. Fine. Remember this, right? How far it goes? Square root of dt. And that is something I'm going to use in a second. Okay. Now, on the very left, I have rotated the MOSFET 90 degrees. So, first of all, you will see the silicon substrate on the left, on the top curve. The yellow region is the silicon dioxide. And the right side I have written as poly. It could be a metal also, the metal gate. Now what happens, do you see that I have also drawn some silicon hydrogen. There are of course lots of silicon oxygen bonds there as well, right? Do you remember only a fraction of them are silicon hydrogen? But I have just drawn the silicon hydrogen one without the silicon oxygen one. And so with some arrows, I have shown that some of the hydrogen is going away. Going away, why? Because I have applied an electric field, there is a strong electric field, and therefore the bonds are being broken and then they are diffusing away. Now, if I wanted to know how many hydrogens are diffusing away, remember, then I will get the number of interface traps, then I will get the QF, and then I will get the delta VT. So that's my game plan. So how many bonds are being broken? I can write a simple equation. You see, no rocket science here, very simple. dNIT dt is the number, NIT is the number of bonds that got broken. dNIT dt means number of bonds that got broken per unit time, is equal to Kf. Kf is some dissociation rate at which the bonds are being broken, depends on the electric field. N naught is the number of original silicon hydrogen bonds I had minus NIT. So N naught minus NIT is number of unbroken that I still have. Okay. Now of course, once they are broken, the hydrogen is broken, they will be walking around. Some of them will be going away, diffusing to the right and going away. Some of them will come back and see that there is a dangling silicon bond sitting there, and it will come back and anneal that bond, because it is around and there is a dangling bond, so it can just do the original forming gas anneal. It can again do the passivation. So that's the second term on the right of the first equation. Now you will notice that I have written NH0, H for hydrogen, NH means number of hydrogen, 0 means number of hydrogen which are at the interface. Because the hydrogen which are diffused far out, they cannot tie up any silicon bonds, right? So it has to be whatever number which are on the surface. Now most of the time the rate is very, very small, and the number of broken bonds is also relatively small. So compared to, so you can set dNIT dt equal to approximately equal to 0, right? Approximately equal to 0. And you can neglect in the first term the red NIT, N naught minus NIT, NIT is small, let's say. N naught is on the order of, do you remember what this number was? 5 times 10 to the 12. I showed you in the last class or the class before. And NIT I'm thinking about on the order of 10 to the power 11. So it's less than 1/10 of it. So I can drop that one also. That gives you the second equation. Do you see that? Kf N naught, I have taken the Kr on the other side, divided it throughout, and so I have a relation between NH and NIT. Two unknowns, these two are unknowns, one equation. Okay. Now, this is the crucial second step, and see whether you can understand it. There's a number of bonds that got broken, right? Hydrogen got away. Now, those will be diffusing, and you can see in the second plot, I have shown how far they will diffuse at a given time, square root of dt. That's how far the hydrogen has gone, right? Okay. Now, the area under the curve is equal to the number of hydrogen which has been released. Now, where will the hydrogen come from? This is coming from because bond got broken. So, the number of bonds that got broken is equal to the number of hydrogen that was released in this oxide region. So, therefore, I can write this following statement and see whether you agree with this statement. NIT, number of bonds that got broken, is equal to the area under this curve. Half, you see, triangle, right? Half. NH0 is the ordinate, and for time t, it got DHT is how far it diffused, the hydrogen how far it diffused. So now I have two equations and two unknowns, right? And that immediately tells me the number of broken bonds goes as, so that was the experiment, by the way, and look at that, t to the power 1/4. So it is telling you by very simple, this 3-line of algebra, no rocket science here, and it's immediately telling you the number of bonds that will be broken as a function of time, meaning that, let's say, this is 1 month after you bought your computer, 5 months after you bought your computer, so you put 5 months in time t, and that will tell you how many bonds got broken. You put it in your threshold voltage calculation, that tells you how much the threshold voltage got shifted and how much current reduction happened as a result, right? So therefore, this is what people do before they sell a computer. They do the extensive characterization and they find out that how it's going to degrade. That is only how they will make a computer and sell it, realizing that you will not bring it back before a certain period of time. Now remember this, NBTI, if you go to interviews and other places, people will be very impressed if you know how this works and what happens, the physics of it, because this is one of the most important reliability problem today. Let me give you some example. This was about silicon hydrogen bond dissociation, right? Many times you will have also hot carrier degradation, that when you turn the transistor on, very large drain bias, the electrons in the drain is very hot, right? Because of the long voltage drop. And when this hot energetic electron comes in and strikes next to the silicon dioxide surface, then silicon hydrogen bonds are also released. So that's hot carrier degradation. Another very important reliability problem, but it was more important in 1980s, no longer as important now. Maybe I'll explain that statement a little later. Now let me give you some examples about silicon oxygen bonds, and in silicon oxygen bonds and the dissociation of it. So starting with gate dielectric breakdown. Now in the gate dielectric breakdown, the first thing before even gate dielectric breakdown happens, first thing you realize that many times the oxygen in silicon dioxide is not where it should be. And so there is a trap level because the oxygen is not where it needs to be. As a result, when the electron goes, instead of going straight from source to drain, many times it gets trapped in that trap level within the silicon dioxide. And as a result, if you have a series of electrons trapped, then you see in the bottom figure, I have that red arrow. That red arrow is the amount of trap charge, right? And if you have over a period of time huge amount of trap charges, as the electrons are going by, a small fraction of them are getting trapped into this vacant sites, and as a result, over a time what will happen? The arrow, magnitude of the arrow will keep rising, and that will change your threshold voltage. You can see that Q ox at x1t, that's a time dependent thing, so that will change your threshold, and as a result your CV curve will shift and VT will shift, and there will be a problem in terms of drive current. So that's one problem. For thick oxide, it's a big problem. But these days, they make such good quality oxide, such fantastic oxide, that number of these defects are minuscule these days, very small. However, there is another trouble. The trouble is that although you initially didn't have any defects, but remember, you are applying an incredible voltage on this. I often say that if you apply 1 volt on 1 nanometer, that's like a 10,000 times larger than the high voltage power line that you see going next to your homes, right? If you see a bird sits between those two, they'll be fried, instantly be fried if you have sits in a power line. And this is about 10,000 times more voltage than that, electric field than that. So you can realize that over a period of time, there'll be bonds will be broken as a result and defects will be formed. And you also realize so that when a certain amount of defects have been formed, these defects which are shown here in little red boxes, those defects might line up. And if they line up, then you have a short circuit between the substrate and the gate, and the electrons will simply flow out. Your MOSFET is gone, no longer a MOSFET, maybe a very bad bipolar transistor you have now with a base contact. And so what you see in the gate current as a function of time, again this is the use time. As a function of time, the gate current remains essentially unchanged for a long period of time. And then all of a sudden this red defects line up, all of a sudden the current shoots up. And there will be such a violent current rise that most of the time the transistor will be destroyed. What you see here on the right hand plot is the time to break down. That's what's TBD. It's not to be determined. It's time to break down. And you can see that this is 10 to the power. So that means you can see the 10 to the power 8. 10 to the power 8 is that 10-year thing, right? On the right hand side. And so most of the time experiments will be made. First, let's look at the red one, VG1. And on the y-axis, I have F, capital F. F means fraction of the oxides broken. So that means, let's say you start with 100 transistors. The first one breaks. So the F is 1 divided by 100. This is a cumulative failure. Then the fifth transistor breaks. So F is 5 divided by 100. So y-axis is you note when the transistor broke, and in the x-axis evaluate that function. It's called a Weibull distribution. So evaluate the function and put a dot there. And you keep putting the dots. And that creates this straight line, in the red straight line. Similarly, if you reduce the voltage a little bit, then you can get the blue one. Why? Because, if you reduce the voltage, defects will form a little slower, and so it will take a little bit more time for the bonds to break, and as a result, it's shifted to the right, a little bit to the right. By the way, where I draw a dotted line, that's sort of where 50% point is. 50%. This is a very strong log-log plot, so therefore 50% will happen about there, and also the green is a little lower voltage. So you do it at 3 voltages, and you see they are all parallel. So if you want to say what will happen at 1 volt, then you will simply extrapolate to 1 volt and see what will happen. Now this point where the bottom horizontal line is, that is 1 part in 10 to the power minus 12. That is this point. And that is because every company wants that if you sell 10,000 IC, no more than 1 should come back. Now, every computer may have a billion transistor, 10,000, right? So this number would be on the order of 10 to the power 12 to 10 to the power 13. So you have to make sure that this time, where this magenta curve intercepts the black curve, that is actually more than 10 years, because you don't want anyone bringing their computer back to you for money back more than 1 in 10,000 persons. And so therefore you cannot accept more than 1 in this number of transistors to fail, because as soon as 1 transistor fails, the whole IC is gone. And so that person is going to bring back his computer. And so we want to explain very quickly what the physics is of this. In order to understand that, there are these 2 things that I'll quickly explain just qualitatively. One is that when you apply a positive bias, this is a MOSFET. Bottom part is the substrate, what I call cathode. Oxide you see, and the metal or the polysilicon is on the top side, you apply a positive bias. So these days, what will happen, that electron will tunnel from the substrate to the gate, and they will come back. They will have impact ionization there, and the holes will come back in the reverse side, and in the process of coming back, they will break bonds. And this is called an anode hole injection, because holes are coming back from the anode region. Now, you don't really have to follow the details, because I will not be asking you to make calculations. Just get the flavor of how people do such a things. Now, so therefore, the time to break down simply depends on the number of electrons that are flowing through, right? Because that determines on how much impact ionization will occur. So that's J sub E on the denominator. And alpha, or A, is the number of electron hole pairs that was generated per injected electron. And then Tp is the number of transmission probability of the holes for coming back. So if you have more holes, then your lifetime will be shorter, right? That's all I'm trying to say. And NBD is the number of defects that you need to create a short circuit between source and drain. So that's the calculation one does. And this is the trap generation efficiency. K is the trap generation efficiency, because every hole cannot generate a trap. So a fraction of them will be able to do that. So from this type of calculation, people say that they determine that when will the oxide will break. But remember, this one is saying every oxide should break at one time. If your given gate voltage means J is a constant, A is a constant, Tp is a constant, but that simply saying that everybody should break at the same time point. Now let me just quickly explain one thing, that what type of dependency do I expect. So if the voltage is very high, then do you see that the top expression for Je is given by this Fowler-Nordhamm type expression. This is a tunneling current expression. A exponential of B divided by E. Alpha, the number of electron hole pair that is generated per injected electron, is the order of 1 and 2. Tp as high energy is more or less a constant. So time to break down goes as inversely with the electric field. Multiply these three out and take the inverse, and then you will get that it will go inversely with the electric field. That's one. If the voltage is low, then the tunneling current has some complicated dependence on the electric field. The impact ionization has this particular expression for the voltage dependence, and therefore at low voltages, the time to break down goes with V, the voltage V. The point is that there is certain electric field dependence of what the lifetime is going to be. Now let me explain this final one about TDDB, because not all of them are breaking at the same time. So if you look at the rate points, that they fail at different times. So how would you determine how they are failing? In order to do that, let's start on the top side. Now probability, this is just high school algebra. So let's start on the top side. Probability of a field column with a rate field column. What is the probability? If the probability of individual one is P, and if there is M rows, then P to the power M, or sorry, Q to the power M. That is the probability of a field column, because all of them have to be present. Now, the probability that you will have exactly one breakdown spot on the left hand side is called P1. Now you see, this vertical column, the rate column, could occur anywhere within all the columns, right? So you take NC1, that is, you say choose one out of n vertical columns, then P to the power 1, because one cell is taken, and 1 minus P n minus 1. What is that? That the remaining n minus 1 are not shorted, right? That's simple binomial expression. So if you simply take that one for P1 and do it for large n, you can show that the P1, and this, try to do it at home and see whether you can express the P1 as equal to chi exponential of minus chi, with the chi given by the following value, just when you have large n. And then the F1 is essentially the probability that, cumulative probability, it will be equal to 1 minus P naught. P naught is the probability of not failing. If the P naught is the probability of not failing, then F1 says the probability of failure at a given time. So you insert that value for P1 in the other one, and that will give you this y as a function of logarithm of time with a certain slope. So people can, in fact, the point I'm trying to make, you can do this at home, but the point I'm trying to make here is that both the voltage dependence as well as the slope of this curve, people can easily calculate on the back of the envelope calculation to predict oxide reliability. Okay. Now very quickly about radiation damage. Now what happens for radiation, and this is for a flash memory, charges are stored in the floating gate called FG. Now what happens is that when a radiation strikes, one of the very large charged particle comes in and strikes, it's so energetic that it creates a shower of electrons and holes. It creates a showers of electrons and holes there. I'm not sure whether you can see it from here. There's a track starting from the top, and as it is losing energy, the energy is huge. It's 58 mega electron volts, and as it is coming down, it is generating a shower of electrons, and this shower of electrons causes huge amount of damage in the oxide, and that again traps charges, causes threshold voltage shift, and again causes reliability problem. So every time you take a flight across the country, this is happening to your computer, that particles are striking, and because planes move about 40,000 feet, right? 40,000 feet, 36,000 feet is sort of 90% of the atmosphere is within at 40,000 feet. So you are sort of exposed to a huge amount of radiation that's coming in. Not huge in terms of meaning that will going to kill you, but huge in terms of it will going to flip some cells on your flash drive. And depends on the energy. See, that was 8 MeV electron, and this is a chlorine atom and coming in, and you can see a huge number of electron hole pairs. It's like explosion has happened. Projectile has come in, an explosion has happened, creating a large amount of defects in your oxide. Whichever gets stuck, that's dead. Again, what happens very simply, and this is a very old problem, many satellites have essentially been disabled because of this problem, is because when a strike happens, you have a huge amount of electron holes generated. The picture on the left, right, is shown, taken from your book. And what happens that the electrons, very quickly, because of the electric field, very quickly it leaves. But the holes are not as fast. They are more heavy. And so it takes a certain time, and then they can generally get trapped and become like an interface trap. So this is that QF, the fixed charge at the interface. And what will happen that although the charge radiation has gone away, but the blue arrow is indicating that the trapped holes will be there for a long period of time, just sitting there, shifting your threshold voltage. And as a result, that transistor you cannot turn on anymore. If you cannot turn on that transistor, then for a given supply voltage, then of course your computer is not working. So, so this effect in thin oxides, of course, this picture is taken from 1970s, but these days oxides are not this thick. So many times the trapped charge effect is not as important. But what happens, because the radiation that deposits so much energy, that many times it ruptures the gate. Gate is very thin. You have 5-6 atoms. Particle comes in, it breaks all the bonds and shorts the substrate to the gate. So that's a slightly different problem. That is the radiation-induced gate rupture. Looks like all biblical references here. And so let me summarize. So that the reliability is really a serious concern for MOSFET, and in fact this is one of the first things that you realize going from university to a company, that you really didn't really understand the details of the reliability physics unless you begin to understand the reliability problems. Now there are many different degradation modes, and people have developed very nice models of predicting those individual phenomena, and they can in fact predict very well that how your transistors is going to degrade and how it's going to behave in 10 years time. Now at present, as I said, NBTI is the most important one, negative bias temperature instability. This is not the sodium problem, right? This is associated with silicon hydrogen bond dissociation. And this is the most difficult reliability problem, and followed by HCI, hot carrier induced degradation, which I did not discuss, gate dielectric breakdown, which I showed you how this is done, and radiation effects. Radiation effects because most of the interplanetary missions are nearly impossible, satellites and other things. You really have to work very hard to make those work under those harsh conditions. So that's it. Okay. Thank you. MOSFET, right? The MOSFET, the two vertical columns are source drain contact. The fingers, the black fingers coming from the two sides are source and drain. The very thin region in between, the thin region is oxide, and the black, little black strip on the top is the gate contact, so gate metal. So you can see that those regions are heavily doped, show us as black in this picture. And if you blow up that region, many times you will see the gate oxide has been completely blown because of the harsh operating conditions that the transistor finds itself in. Incredibly, the physics of this is actually one can calculate when things will break after a certain period of operation. That's the essence of the reliability physics. So in order to understand that this reliability, issues of reliability, you will have to distinguish between two types of bonds. One bond that I have already discussed is the passivation of silicon with hydrogen at the silicon dioxide interface. This is that forming as anneal. Remember that silicon dioxide cannot really satisfy all the bonds of silicon. Therefore,
nanohub.org. You can follow along with this presentation using printed slides from the NanoHub. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
So today we'll be talking about reliability of MOSFET. This is a very important topic. Most of the time for last 10 lectures or so, we had been talking about how MOSFET operates, MOS capacitor, MOS transistor, how it operates. But most of the time what people do not realize that what makes a technology successful is not how much it performs or how well it performs initially in the laboratories, but how well it survives the harsh condition that it is supposed to operate over a prolonged period of time, many times for 10 years or so. And that is exactly what reliability of MOSFET, the physics of it, tries to describe. So I'll begin by explaining why this is a very important problem. Turns out one of the most important problem in MOS technology these days is the reliability of MOSFET. I'll explain why. We'll talk about three types of reliability problems. The most important one is something called a negative bias temperature instability. Now this you should distinguish between this bias temperature instability I talked about the sodium ion moving from within the oxide left and right, coming from human hand and how it was solved in 1960s to solve and make MOSFET possible, practical MOSFET possible. This is different. This is also discovered in 1960s. It went away for about 20-30 years, and then in mid-90s it resurfaced, And nowadays, this is one of the most important reliability challenge for MOSFET. I'll talk about gate dielectric breakdown. As I said, that this is a very thin oxide that you have about a nanometer or so. And when you apply a voltage, 1 volt may sound small, but you see, if you divide 1 volt divided by 1 nanometer, you have more than 10 megavolts per centimeter electric field in there. If you look up in any book, then it will say at 10 megavolts, this should break down completely be destroyed. Yet, our transistors do not get destroyed. And I'll try to explain very briefly why and how to think about that problem. Finally, this issue about radiation-induced damage, particles coming from sun and outer space, and as well as various environments. This is very important. Every time you take a transatlantic trip, there is a probability almost close to 1 that one of the bits of your flash memory drive will be flipped. So that if you take a PowerPoint or any file, your music file, it's almost certain that a few of the bits might be flipped. And the reason it doesn't hurt you, because there are error correction code that you have to put in every storage device now because of this bit flip problem. I'll explain a little bit about that also before concluding. Now, the point I wanted to make in the beginning, that in this course you are learning about how MOSFET operates, right? And how to analyze them, how to think about surface potential, inversion charge and all. But of course, what you realize that these MOSFETs are under incredibly harsh conditions they operate. Then by the time you throw away a computer, almost all the transistors will have switched close to about 10 to the power 14 number of times. 10 to the power 14 is a very large number. It's like 100, 10 to the power 14 is about a, how is it, 100 million? Oh, no, not million. Okay, you get the 10 to the power 14. It's a large number. I forget how else to put it. And when you turn things on and off this large number of times, this is a hard disk reader that all of you have in your computers, and you can see on the periphery there are all input-output MOSFET transistors that essentially connect the output world, the outside world, to the inside world of the microprocessor. And you can see that they have been lighting up. This is a liquid crystal image of the temperature, and they have been lighting up. That means those places are incredibly hot. And what will happen that when you use it under such a harsh conditions over a prolonged period of time, the transistors are going to degrade, and essentially, eventually, they are going to fail. And this is certainly not acceptable, because once you have this type of degradation, let's say the gate oxide, you remember the MOSFET